right, let's get started. Who's awake? I got you a little awake with that wave, right? I got to tell you, that was not my idea. That was my colleague Simone's idea, who did this before, but she did it in a football stadium, which was kind of cool, I'd say. So now we're awake, I'm going to test whether you're really awake by asking you a question. And this question is, what do you see on the screen behind me? Where was this picture taken? If you know, shout. Ooh, SpaceX, the first one, right away. Yes, this is a picture from SpaceX, and well, it looks kind of cool, right? There are all kinds of screens, and you video feed of a rocket, probably. So if anyone is building distributed systems, it's probably SpaceX. So that sounded interesting, so I browsed through their career pages yesterday to find out like what type of profiles are they looking for. And they're building stuff in all kinds of languages, Java included, but I also saw JavaScript in there. So it may be possible, well, it is possible that some of the software at SpaceX is built in JavaScript. So it may be possible there's JavaScript running in space. Which sounds kind of scary. But on the other hand, the further away from Earth JavaScript is, the less damage it can do, right? Just kidding, I love JavaScript. So when I created this talk and I first practiced it, I had about 2 hours of material. Who has 2 hours here? Well, there are some, but most of you don't have. But I shorted it, and we should be able to do it in 49 minutes. So we should also call this the good parts that I borrowed from the JavaScript book. As you see, I love JavaScript, but only the good parts. Or we could call it Networking 101, because I'm mainly going to dive into networking. Or even how the internet works. So before we dive into the good stuff, let's start with why. Why this talk? Why are you all here? Because I'm almost sure that almost all of you are in some way involved with building distributed systems. I believe microservice is the popular term for it now. So even if you're developing a static website, it's still a distributed system involving a browser, a network connection, and a web server. And in this talk, we're mainly going to talk about those network connections. So my name is Bert Jan Schrijver. I work at Open Value. I was checking if my colleagues are awake. 2 of them are. I also do some stuff for the NL Jug. Do we have people from the NL Jug in here? Yes, that's a loud bunch, right? So as you can see on the picture as well, I wave my hands a lot. I'm also on Twitter, where I spend way too much time. So I'll share my slides there afterwards. And if you have any questions afterwards, feel free to reach out. I'll probably reply way too fast. So the next 45 minutes, we already did the why. So we're going to start with some theory, because you can only fix something you can understand, right? So the first part will be theory, and the second part of the talk will be a bit more hands-on. So we're going to talk about what are distributed systems, and why are they difficult, why it's difficult to work with distributed systems. I'll share I'll dive into networking 101, so how do networks work. I'll share a structured approach to debug distributed systems. There'll be lots of demos. Hopefully you have time to share some war stories about things that went wrong in the past. And every story needs an end, so this one has a conclusion as well. So this talk is mostly about debugging connections between systems and about the messages that are being passed. So let's start with what. What is a distributed system? Well, if you want to know what something is, you go to Wikipedia, right? So that's what I did. Wikipedia says, it's a system whose components are located on different network computers. And they communicate and coordinate by passing messages. So we're going to talk about components on different computers that talk messages. So what are characteristics of distributed systems? Well, they have multiple components running concurrently in different places, maybe even different parts of the world. There's no global clock, which doesn't sound like a big deal, right? Who cares about clocks? Well, stuff like logging and in-order delivery, maybe metrics depend on clocks. Time in distributed systems, especially when you're distributed across the world, is not really reliable. Actually, because quartz crystals that are using these clocks, they tend to drift. And components can fail independently of each other. which means that at some point, if your system is big enough, you can be pretty sure that at any point in time, at least some parts of your system are broken. And as a result, distributed systems are harder to reason about, harder to fit in your head. And as Martin Kleppmann says, he's the author of Designing Data-Intensive Applications, which is an awesome book if you want to learn more. He said it's fundamentally different from writing software that runs on a single computer. And the main difference is that there's new and exciting ways for things to go wrong. So we're going to look at those exciting ways, right? So why do things go wrong if we build distributed systems that are difficult to reason about? Well, one reason is that we tend to make false assumptions about those systems. These assumptions are called the fallacies of distributed computing. So they're things that we tend to make wrong about distributed computing. And these were made by a couple of smart people at Sun Microsystems a while ago, and they're describing false assumptions that people who are new to distributed systems typically make. Me included, and you included probably as well. So there are, I don't know, about 8, and they're all false. So networks are typically not reliable. There may be, I don't know, water in your network closet causing your switch to fail. There's always latency, and latency may have impact in messages, timing, etc. Bandwidth is typically not infinite, especially if you're working on mobile connections. This may have an impact on the experience of the end user, for example. The network is secure. Well, there's an interesting story about this. Google has quite some data centers, right? And Yahoo as well. And these data centers are connected through fiber cables that, for example, run below the water in front of the coast. And there's this rumor that NSA had access to data between data centers from Google and Yahoo. So what they did, they dug up a cable, they cut open this cable, put a device in between, and from then on had access to all the data flowing over these cables. So this was before Google and Yahoo had encryption on the traffic between their data centers. So this is one of the reasons why you should encrypt internal network traffic as well, because it may not be as internal as you think. Network topologies tend to change, something that now may be really fast. So you're making a database connection to something close, you have almost no latency, and for some reason the cable breaks and now you're routed through the other end of the world, and now you get 100 millisecond latency on every query. So what is 100 milliseconds? Not that much, but if you're doing 1,000 per second, then it is. There's typically more than one administrator, and different people do different things. It costs something to transport data. It may cost time, it may cost bandwidth, it may cost you money. And the network typically is not homogeneous, which means that some parts of the network may be more reliable or quicker than other parts. So knowing that these systems are difficult to reason about, knowing that we tend to make false assumptions, you may ask yourself, what could possibly go wrong? Well, let's start with something that's probably a long time ago for many of you. Basically, everything that can go wrong is in the OSI model. How many of you have recently studied the OSI model? How many of you have done it like 5 or 10 or 20 years ago? Exactly, I had the same feeling. But basically, this is a good indication of the things you can think about that can go wrong in distributed systems. So let's look at the TCP/IP conceptual layers, because there are only 4, and I only need to explain 4 instead of 7. So the application layer is typically protocols like HTTP and DNS, and also TLS that run basically on the top layer. The transport layer, we're talking about TCP connections, UDP connections. The network layer, we're talking about IP, so routing between machines. And the network interface is physical media, Ethernet. So what can go wrong? Basically, things can go wrong in all of these things. Well, typically, we don't influence all of these things. So has anyone ever had a job interview and had a question that started with, what happens when you type google.com in your browser's address bar and press enter? Well, I'm going to ask you all this question. What's the first thing that happens? Shout. Well, DNS happens, but stuff is happening before. TLS handshake, that typically happens, I guess, after DNS, but way earlier. Think about your local machine. Somebody said keyboard, and that's actually quite well in the right direction. So what happens first is, well, you start typing, right? So you press down a key, and then it depends whether you have a USB keyboard or like a PS2 keyboard, if those even exist. So this typically, when you press a key down, a current flows through your key, triggering probably an interrupt in your system somewhere, instructing the system of a key down press. So why I'm asking this? Because, well, your G key can be broken as well, right? And then this doesn't work. So if you find this interesting, there's this site on GitHub, github.com/Alex, what happens when, and he describes this process in about 10,000 steps. So if you ever have like a rainy Sunday night, you feel bored, you may go here. But what happens when we type Google in our browser address bar? Well, let's take my notepad and start drawing. So let's assume I'm sitting at home behind my computer. This is me. After 4 days of DevOps, I look kind of skinny. This is my laptop. I'm typing www.google.com in my browser's address bar. Press enter. So first thing that happens is my browser is going to parse the URL. It sees www.google.com, then it's going to check its HTTP strict transport security preload list, which is probably in Chrome, and probably it says you can only access google.com over TLS. So now I'm going to check my local DNS cache, do I have an entry for google.com? Let's assume I don't. And then my laptop is going to make a query to my provider's DNS server, which is the first time I'm stepping outside my local network boundaries. I'm now going to connect over the internet to my provider's DNS server. So my computer connects to my provider's DNS server and asks it, can you give me the address for www.google.com? So let's assume, we're making lots of assumptions, that my provider does not have the address for google.com. Well, then it needs to ask the authoritative source, which is probably somewhere in a Google data center. So there's a DNS server there, my provider forwards to Google, Google replies, oh, well, it's address 1234. And then my DNS provider replies to me, and now my machine knows it needs to make connection to 1234. But we know more. We know that we need to go TLS because it was in the strict transport security preload list. So we're going to make a TCP connection to port 443 because it's a TLS connection. And this connection is going to go through some load balancer at Google probably. So on top of this TLS connection, TCP connection, we're going to make a TLS connection because it's going to be encrypted. And on top of this TLS connection, we're going to do an HTTP GET request for google.com. So it's probably safe to assume that Google is big enough that they have some kind of service registry in their network. So the load balancer then asks the service registry, tell me where I can find the machine that handles HTTP requests for google.com, which is probably a Kubernetes cluster or a Borg cluster at Google. And there's probably some ingress load balancer in there that talks to a service registry as well. So it asks the service registry, let me know which internal host I need to go to handle HTTP requests for google.com. It connects to some internal host. On this host, there's probably a Kubernetes pod running, and this pod probably needs some database access to connect, so it connects to a database, fetches some data, and then replies with the HTML for google.com, which travels the same route all the way back to my laptop with the HTTP response. So the steps we just described are make a connection. So this is both IP and TCP and TLS and HTTP. So we almost had the entire OC model. Make a request, and then parse the HTTP response we get. Simple, right? But the point is that things can go wrong in all of these arrows and boxes. So you may ask yourself, where do I start when something is wrong? Well, here's an approach I've adopted over the years. It's not necessarily the right one, the best one. It's one that works for me, and it may work for you as well. So it's a couple of steps, and we're going to look at them in more detail soon. So it's about observing and documenting the situation, creating a minimal reproducer, start debugging on the client side, check whether the network connection works, so check DNS and routing, check the actual TCP or UDP connection, inspect any traffic or messages that are flowing, debug on the server side, and hopefully you find out what the problem is, and then in the end you can wrap up and do a postmortem. So let's start with step one. observe and document. So think for yourself, what do I know about the problem? Something is not working, which information have I gathered? Try to enrich this information. Inspect any logging you have, errors, metrics, tracing of requests. And then draw on a whiteboard or a piece of paper or a napkin, draw the path from source to target. And think about what's in between and focus on details here, because the problem may be in a system that you don't control. There may be some firewall or proxy in between that's messing with your HTTP headers. So make sure that you focus on details there. And then ideally also write this down in some sort of document. So this document helps building insight and also helps you to transfer knowledge to others. Whenever you need to onboard somebody else on your problem, you can give them a document and have them up to speed in 5 minutes. And this is also the basis for the final step, which is the post-mortem, where you look back and describe what went wrong. And think whether you can reproduce the problem in a test, in a unit test, an integration test, for example, by injecting errors on your local site. So tools you use here, maybe a whiteboard, documentation, logging, metrics, tracing. You could have a look at the Open Tracing project, tests, or fault injection systems like Jepsen. So if you're building distributed systems, Jepsen is an awesome tool to inject faults, latency, error, etc. And the result may look something like this, or completely different. So step 2 is to create a minimal reproducer. So a minimal reproducer is something that can reproduce the problem with the least amount of effort and time. So your goal there is to maximize the amount of debugging cycles. So you've probably all experienced that a colleague says they have a problem. And I said, okay, can you show me the problem? And I said, yeah, I just need to go here, click here, log in there, download this, copy it there, run it on my desk 4 times, and then press this button and do that and telnet here, and this is the problem. And it takes them 15 minutes to show the problem. So if it takes you 15 minutes to show the problem, you can only try 4 times in an hour a solution. If it takes you 1 minute to demonstrate the problem, you have 60 tries. So the goal is to maximize the amount of debugging you can do. And also, you probably hate waiting, so it also helps. So focus on short development iterations and quick feedback loops there. And get close to the action. So try to get as close to the problem as possible. If it's happening on some remote server, you may need to go to the remote server, log in there. It may help to, I don't know, build a simple Java app or a shell script that you can run somewhere that's close to the action. Getting close to the action may also mean that you need to be close to the target machine, for example, by jumping there over an SSH tunnel. Who knows about SSH tunneling? Oh, that's about half of you. Okay, so then for half of you, this is going to be boring. For the other half, let's do a quick demo. So let's say that I want to debug something that runs on my web server, on a remote web server. And I don't have access to this because it's a firewall or internal port. So if I now, is this readable on the back? Yes? Okay. If I telnet to my local machine on port 8080, well, there's nothing running now. But let's say that I want to debug something that's on a remote machine running there on some internal port that I can't access. To demonstrate, let's abuse the OpenValue web server. So I'm going to set up an SSH tunnel that will open a local port, 8080, so this is local on my machine. Then I'm going to jump to the web server, which is the remote server. And over there I'm going to connect to localhost. So this is not this localhost. It's the localhost on the remote machine. And it's going to connect to port 80 there, because that's where the web server runs. And let's log into the remote server. So now if I telnet to localhost 8080, I get a connection. And I can even talk HTTP. You do this every day, right? Oh, and it says me, buzz off, you need to be on a TLS connection. But still, I got to connect to some remote host. And obviously this is a trivial example because this machine is also reachable from the outside. But you may use this to use some machine in between to jump close to the action to, for example, get a connection to your database server. So tools you use here, maybe your IDE, shell scripts, SSH tunnels, curl, whatever you can do to get a quick reproducer of the problem. So next step is to start looking at what's happening on the client side. So let's assume that a connection is something between a client and a server, right? Or a consumer and a producer, but there's typically 2 systems involved. So focus on eliminating anything that could be wrong on the client side. So think about, am I connecting to the right host at all? Do I send the right message? And do I receive a response or not? And this is not much different from local debugging you would do on your local machine, apart from the fact that the client could be running on a remote machine as well, right? If it's some service that has a client that you're trying to debug. So try to get as close as possible to the network boundary to figure out what's going wrong, because there may be the message may be corrupted somewhere in your client already. And is the issue already present when you receive the response from the other end? Or do you somehow corrupt the response when you're getting it back because I don't know, your JSON deserialization is broken? So tools you use here are your IDE, a debugger in your local client, and maybe logging. You could also add extra logging to inspect whatever's going on the client side. For example, to log any network traffic that you're getting in. So step 4, now it's getting fun because we're now getting to the outside network boundary. So first check that you're actually doing the right DNS query. So typically we're connecting to machines based on host name, right? Some name, some domain, some top level domain. And this resolves to an IP address, and then your machine connects to this IP address. So make sure that you absolutely know to what IP address the host name that you're trying to connect to should resolve to. Because not more than once there's some kind of local DNS or cache or whatever that is giving you the wrong IP address for the host that you're trying to connect to. And verify that this actually happens at the client. So verify that the client has the same idea as you about what would be the right IP address to connect to. And we're going to do a small demo there in a bit. And about routing, verify that your machine can actually reach the target machine. So verify that you, for example, can ping the target machine, or that there's a route from you to the target machine. There's no firewalls in between. So let's start with playing with DNS a bit. Let's say that again I want to connect to my web server, I want to do a HTTP request to my web server. So I can fetch host is a tool you can use for DNS queries. Going to fetch the IP address for this web server, and it says, well, it ends with 58. Okay, but this is probably answered by either my local DNS server or my provider's DNS server. In this case, Devox's provider's DNS server. So does this actually have the right data? Well, who do you ask if you want to know? You ask the authoritative source, right? So let's find out what are the name servers for this domain. Well, it says it's 3 name servers at antagonist.nl. Okay, this is still a name server replying. Who's the authoritative source for NL domains? This is the Stichting Internet Domeinregistratie, which is the root DNS server for the Netherlands. So let's query the Internet Domain Registry for the Netherlands. And here it's saying, okay, it's the same server. So probably the DNS service I'm using is the right one. So now I can query one of these DNS servers to check whether it's giving me the right IP. So I'm saying, give me the IP address for this host, but deliberately ask this server. And luckily, it's giving me the same address. So maybe I may be interested who owns this IP address, and this can give you some information as well. So we can do an whois as well on IP addresses. And this tells me this is an IP address owned by Amazon EC2, so it's probably some machine running on Amazon. So you can use host basically to query most DNS entries. There are also different types. So we now, when you do a host, you check for an A record, which is the IP. We tested the NS record. Let's see what happens if we query dns.google. These are the Google DNS servers that you can use in your home to get a quicker DNS service. But you can also ask for text records. So DNS text records are records that, well, you can store text in a DNS entry. So let's see what's in dns.google. So there's a sender policy framework, which is for mail. And there's a link to an XKCD comic in the dns.google DNS entry, which I found interesting. So let's see what this points to. And I'm going to have you read it for yourself. So I guess this is the kind of humor that DNS administrators have, right? All right, so we now want to make sure that we can actually, so now we know which IP address to reach. We can now see if we can actually reach this IP address. So we can do a ping. So ping sends an ICMP request, which basically is a request that sends like a hello to some remote server. And if the remote server feels like it, it will reply. And it tells you the latency. So I have a round trip of about 10 milliseconds from my machine here to the devox.be website. So I know that it's reachable. If the ping doesn't reply, this doesn't mean too much. It may also mean that the machine is blocking our ping reply, so don't worry there. So if I want to know which network path my machine over the internet has to the other remote machine, I can use traceroute. So let's go to my favorite domain, disney.com, and see what happens. So this is quite fast. It may take a bit more time every now and then. So here's all addresses started with 10, which are reserved, probably which are reserved addresses, right? Let's just check. Who is? And then this address. It's reserved for private use. So these are probably also internal addresses that are used in the Devox network here. So then I'm going to AMS6, which is the AMSnet Internet Exchange. I'm going to a core Google router, and then it's going to some Google userscontent.com site. So probably I'm hopping to Amsterdam, and from there, going over one of the cables that Google has that NSA has their wiretap inserted. So I better not go to this site, or NSA knows that I love Disney. So if you want to check like more stats at the same time, you can use a web-based tool called nslookup.io. So let's say that we want to inspect devox.be. Let's see what happens. So we see some addresses there are multiple addresses. There's some Google text ownership verification. The name servers are linked to Cloudflare, so probably Devox uses Cloudflare to make sure that you don't DDoS their site whenever the registration opens. Their mail is at Google. Well, and we can also check some other DNS servers to check which answers they will give. And another tool you can use to check DNS around the world is dnschecker.org. So in dnschecker.org, you can enter a host name, and then it will give you, it will query servers around the world telling you which IP address they reply to this query. So in the case for openvalue.nl, it's the same one, because, well, we have a quite no-nonsense website. It resolves all around the world. But devox.be is on Cloudflare. So let's see what Cloudflare does. So we're getting, well, quite some different IPs. So probably because Cloudflare has points of presence all around the world, right? And from every place in the world where you make a query to devox.be, you'll be routed to probably the closest point of presence from Cloudflare. So this can give you some information about worldwide resolving. So if you're ever into trouble with, you know that a server is giving a false reply, you may be able to ask them to clear DNS cache. So Google has a site where you can clear their Google DNS, and OpenDNS also has a site where you can ask them to clear the DNS. So tools you may use here are host, nslookup, which is a similar tool to host, dig, you can use also to do DNS queries, whois, ping, traceroute, and these two web-based tools. So next we're going to check the connection. So can we actually connect to the port where we want to connect? And if we cannot connect, do we get a reject or a drop from the firewall? So reject means actively saying you cannot get in, and a drop means silently dropping where you won't get a response. And this means two things. So if you get a reject, then there's nothing running on the port. If you get a drop, the firewall is dropping you. I'll show in a bit. So this is a connection open and stay open. If it immediately closes, there may be some firewall or proxy in between. Are we talking TLS? So is the connection encrypted? If so, it becomes a bit more difficult. And what is the connection speed between us? Is the connection fast enough? So let's dive in there, but not before I give you a public service announcement. And this public service announcement is think about firewalling traffic on your machines. And when we do this, you typically think about incoming traffic. But think about firewalling outgoing traffic as well. So by default, most machines you have in your server room or in your cloud, they don't need to be able to go to the internet to go shopping on Amazon.com or to DDoS another machine. or make outgoing JNDI connections to some rogue Log4j server, right? So if ever you're installing a new server, try to block any outgoing network traffic. If you do need to go outside, use a whitelist. So let's say that we again are going to debug some network connections. Well, if I'm connecting to our web server, port 80, well, then it connects. So now I have a connection. If I connect to port 81, nothing happens. So this is a drop. The firewall is dropping my request. So now I know that either cannot reach the machine or that there's a firewall blocking my request. If I connect to localhost 80, I get a connection refused, which means I can connect to this port. It's not firewalled, but there's nothing running there. So if we want to know about whether my connection is fast enough, well, there are a multitude of speed test tools you can use. I like to ask the University of Twente for a file of 1,000 megabytes. And we can see that on this connection I have a speed of around 1800K per second, which is reasonable for a public Wi-Fi on Devox. So good job, Devox. But sometimes you may want to measure the connection speed between two servers. And there's a nice tool you can use there. So for this, I'm going to log into 2 machines, which are in my home. So hopefully my home is connected to the internet at the moment. That one is. And let's connect to another server as well. So on the server on the left, I'm going to run iPerf, which is a internet performance tool. It's going to run in server mode. And the server on the right, I'm going to run as well. And this is a client, and it's going to connect to the IP of the machine on the left. So let's see what happens. 8 gigabits, 14 gigabits, 7, 12, 8. That's pretty fast, right? It's somewhere between, I don't know, 5 and 15 gigabits. But I only have a 1 gigabit connection at home. Why is this so fast? Because I'm cheating. Because the machine on the left, on the right, is a VM running on the machine on the left. So it's local network traffic. But iPerf is a tool you can use for measuring the peak network performance between 2 machines. So if ever you need to connect somewhere and you cannot connect, and it's a cloud machine, and you have the feeling that everything is set up right, use the advice of Arno, a former colleague from me, and Arno used to say, "Ein kaltes Boot ist immer gut." So reboot the machine, and when it reboots, it reinitializes the network, and then typically the network configuration is applied again, and then you're good to go. So tools you use here are Telnet, Netcat, which is comparable. So Telnet basically makes TCP connections, Netcat as well. You can use curl to make HTTP requests, use iPerf to measure network performance. So now it gets interesting, because now we're going to inspect the traffic and the messages that are flowing between systems. So make sure that you know that you send the right request. And again, check this as close as possible to the network boundary. Do you receive the right response? How do you know? Do you handle TLS or not? So if you need to debug encrypted connections, well, you need to step up your game a notch, because it's a bit more difficult. You either may use a man-in-the-middle proxy that you install that decrypts traffic, inspect it there, and then re-encrypts. Or ideally you try to sit between the point where TLS terminates and the actual server. So typically, if you're running a Spring app on a machine, there's probably some load balancer or an Ingress or an Nginx in front that handles TLS traffic for you. So the connection is TLS until there, and this one terminates TLS connection and then goes over plain HTTP to your Spring app, usually. So in this case, it might make sense to sit in between those 2 connections, because then you can read the unencrypted connection. Think whether there are any load balancers or proxies in between, and they may cause trouble there by mutilating your messages. So let's say that we're going to check some connections again. So in this case, let me stop my iPerf server. In this case, I want to debug some network connections between my machine and a remote web server. So let's start with well, I already showed you that you can do this over Telnet, but that's a lot of work, so let's try curl. And curl our web server. Well, I only get a 301 that says you need to go somewhere else. Okay, so how do we know where I need to go? I'll instruct curl to be a bit more verbose. And now it's saying, hey, there's a location header and you need to be here. Okay, let's go there. Now we see a bit more. So we see that there's a TLS connection being made, which CA cert it's using. There's some handshakes going on. The certificate matches. It's by Let's Encrypt. We're using HTTP2, and then we're making a GET request, and we're getting a HTML response, but also a location. You need to be here. Okay, let's follow that as well. And then we get some HTML back. So if you don't have the possibility to make these requests yourself, you may sit in between your client and your server. So let's say that I'm sitting on my local machine here, and I'm now going to monitor TCP traffic on port 80. I need to be root for this, because, well, not everybody on the machine is allowed to monitor network traffic. So I'm going to listen to anything that happens on port 80. So we see the traffic flowing here, right? This is the actual request that's being made, and this is the response that's being sent that we just inspected as well. So if you don't influence the client, you can still look at the network traffic. So what if we want to do this remote? Would that work as well? Well, let's see. Same thing. We see the same request flowing, right? So why can I see this request? Because it's a non-encrypted request. So I won't be able to do this if it's a TLS request, because then the message will be encrypted. So talking about HTTP responses, they may start with a 2, 3, 4, or 5. One thing that I always use to keep them in mind is 2 means, if it starts with a 2, it means all good. 3 means go away. 4 means you screwed up. 5 means I screwed up. So we talked about TLS debugging a bit already. Well, I could talk for hours about that, so let's not bore you with that, although it is interesting. So tools you use here are curl, tools like Wireshark or TCP-dump to inspect messages. Maybe the network tab in your browser is nice to show, and maybe a man-in-the-middle or TLS proxy. So the network tab in the browser. Let's go to, well, let's say devox.be. Going to inspect. Zoom a bit, network tab. So you see all the requests that are being done below here. So if you want to know more about a request, you can click timings here. Then you see basically timings like for how long was it blocked, DNS, waiting. So in this case, I needed to wait for some reason for 60 milliseconds. DNS took 25. Then I was waiting for 270 milliseconds before the server gave a response, and then receiving it took 14 milliseconds. And then you'll see this data varying over the various requests. And in the end, probably you'll see the blocked becoming a bit more. Maybe not, maybe it's just a really fast website. This one was blocked for a while, probably because I was waiting for some other requests to complete, or I had exhausted my HTTP client connections in my browser. So if you want to play with one of these requests, there's a nice utility that's both in Firefox and Chrome. You can say copy as curl. So if you copy as curl, then you're going to basically replay this entire request and make the request to the server. And in this case, I'm getting binary output because, well, this may give something back that's not human readable. Let's see, find something else. This is interesting. This should be a fairly regular file. Maybe because it was compressed or something. Same thing. Min output, min. Yeah, this is probably gzipped, I guess. But you can use this to change any parameters in this request. So any OAuth tokens will also be in here. So this is an easy thing to further debug a request that your browser makes. All right, we have 11 minutes left, which should work, I hope. So tools could be the network tab or maybe a man-in-the-middle or TLS proxy. So next step is debug the server side. So you should get close to the server, see whatever you can see there. So inspect the remote host. What do we know? Where is it running? Is it Kubernetes? Is it on the cloud? Is it a VM? Is it bare metal? Can you attach a remote debugger to the process? This is actually fairly doable. Takes also about an hour to talk about, but there's a video on our YouTube channel where a colleague of mine explains how you can attach a remote debugger to a remote Java process over a SSH tunnel. Maybe you'll be able to attach a profiler or something like a Java flight recorder to debug what's going on. Or you can channel your internal Linux sysadmin and use strace, which is a debugger for Linux systems, like actually for C, I guess. So how does this work? Let's say that I want to know whether the TLS request we're making, whether that is actually sending the right request. So if I go again to our web server, and I want to monitor port 443, and I do a request now, probably I cannot read it. There's a request going on already, quite a lot. So do we see any data in here? We don't see any requests in here, right? So it's only encrypted data. But what we can do is attach a debugger to the running web server. So to do this, we need to find out the IP address of the Nginx web server, the process ID of the Nginx server that's running here, which starts with 7.4. And I'm going to connect strace to this process, and then we can attach to the running process. This works with Java processes as well. Oh, you see that there's already some stuff going on. So if I make a request now, then we should be able to, or maybe 1,000 people are hitting our website now. Oh wait, for the sake of the demo, please don't make any requests for just a couple of seconds. Let's see if you have the right process. Yes. Okay. Well, still going. I guess we just have a really popular website. So what you should be able to see in here. Interesting. What you should be able to see in here is some requests and responses. So this is a binary file that's being sent. Okay. Here we go. So, oh, that was a nice one. So somebody was requesting a obscure URL. Here, there's a GET request to openvalue.club. That sounds like a cool domain, right? So here's the response above, but you see also that you can see the actual HTML that's being delivered. So we're now reading this from memory at the Nginx process at our server, while the request is encrypted. So even if the request to the service is encrypted, probably will be somewhere in memory unencrypted as well, right? So this is a neat trick to basically read some stuff in memory server side. Will you ever use this? I don't know, but it was too cool for me not to show it to you. So tools you use here are SSH tunnels to connect to a remote machine, maybe remote debugger, profiler, strace, or Java flight recorder. So the final step is to wrap up and write a post-mortem. Hopefully you found the issue. So document it. What was the timeline? When did we first see something going wrong? And how long did it take us to respond? What did we see? So how did we observe that there was a problem? You use this to recognize the problem next time. Why did it happen? What was the root cause of the issue? What was the impact? Did it impact users? If it doesn't impact end users, it's not a big issue in my eyes. How do we find out? So what were the keys we took from the information we had that made us figure out what the problem was? What did we do to mitigate? So how did we make the problem less annoying for users? And what do we do to fix the issue? And what should we do to prevent this from happening again? And I guess this is the most important question you ask in a post-mortem. What should we do in our process, in our tools, to make sure that if this happens again, it won't impact our end users? So tools you use here are a whiteboard and documentation. So Jason Cahoon, the author of the Google chapter in the Chaos Engineering book, he said, if you really want a reliable system, you have to understand what its failure modes are. So you have to actually have witnessed the system misbehaving. So misbehaving systems are my favorite. So we're going to look at 3 cases there. Should work in 6 minutes. So this is the one where it worked half of the time. So the case was we would do a request to an application, and this would generate a document like a PDF, and then return the document to the user. And we saw that this worked about half of the time. So half of the time we would get the document back, the other half of the time we wouldn't get the document back, and the server would say something like, document not found. So what was wrong here? Shout if you know. Caching could be, but it wasn't caching. Well, no, this was not DNS in this case. Load balancing, yes, load balancing was involved. 2 nodes, yes, that's why it worked half of the time. So the problem here was that the system wasn't stateless. So this process worked where you would do a request, and then it would generate a PDF, write it to disk, and then it would be a second request requesting this PDF. But if the first one would go to one server and the second one to the other, you wouldn't get the PDF back. So always try to make your system stateless. So in this case, we solved it by putting it all in one request as a quick fix. The one at a school. So I was building software for an educational publisher, and we were going to a school because they had trouble that our application was slow. We ran on AWS, and everything was pretty scalable, and I was pretty sure that there was no problem on our side. But from their point of view, it was slow. So we went there, and I said, okay, can you tell me a bit about your network setup? And yes, it's really fast. Here is a speed test, and well, that looked all fairly reasonable. And then I said, okay, can you show me what the problem is? So the system admin went to get, it was a secondary school, so we went to get a girl of about 12 years old from the classroom. She came back with an iPad and says, yes, I have the system here, and if I scroll through it, the applications sometimes load really slow, and sometimes, so the images sometimes load really slow and sometimes not. Okay, that's interesting because we host them on CloudFront, and CloudFront is pretty fast. So then I tried to do this myself on my own laptop, and it was indeed slow. So then I went to one of the images that was loading slow, and I tried to resolve this on my own machine by making an HTTP request. And it took quite some time to do this HTTP request, so indeed it was slow. And then I found out that it was when I tried to do a DNS lookup, I found out that the DNS lookup was taking a lot of time. So I asked, like, what's the DNS setup you have here? Oh, it's funny you ask. So why? Yeah, we have 2 connections, so we use Google DNS. So okay, well that's typically quite fast, but still something is going on. And then I asked, how many people are here? Yeah, we have about 3,000 iPads connected. And they're all working at the same time? Yes. I said, whoa, that's a lot of HTTP requests for all those images that are in those lessons, right? Then I started Googling about rate limiting in Google Public DNS. And it turns out there's some kind of undocumented rate limiting in Google DNS, where if you make thousands of requests per second, it will start becoming slower and slower and slower. So I said, okay, let's try OpenDNS. So the admin changed it in their DHCP server, use OpenDNS for DNS responses, and then we asked the same girl back, and it was still slow. I said, oh no. Then I think, oh wait, DHCP, she needs to get a new lease. So she disconnected from Wi-Fi, connected for Wi-Fi, and it was really, really fast. So that was amazing. And the system admin said, oh, we had a goosebump moment. But it was because of a reasonable setup they had, and from their point of view, our system was slow. So yes, it was 0 days since it was DNS. And then this one was cool as well. Our application went down. And upon investigation, we saw that it was because our analytics service couldn't send messages to the analytics collector. Turned out the reason was that the analytics collector was shared by a big Dutch website, nu.nl, and there was breaking news on the website, and this breaking news caused everybody to get a notification on their app, go to the website, and this overloaded the analytics collector. And it didn't respond anymore. But our system was sending analytics to this service. And the service that was sending analytics on our side was filling up its connection and thread pools to go there because it was timing out. So once we scaled to an insanely amount of servers, we had enough pools to be able to survive the issue. But obviously, the long-term fix was to not make your application dependent on something that's not part of your core business. Sending analytics was not a core business. Education was a core business. And also think about integration with external systems. What happens if somebody sends like an error back? Okay, you immediately know. Something timeouts, how long do you wait? Typically 60 seconds by default in a JVM, I think. So think about this use case as well. So, 1 minute left, and we're going to make it. To summarize, a structured approach to debugging distributed systems. Observe and document, and write it down. Create a minimal reproducer. Start debugging on the client side. Check whether DNS works, check that you're routing, check you can make a connection. You can actually make a connection to the host. Inspect traffic and messages going in between. Debug server side, and finally, write it all down, wrap up, and write a postmortem. So I hope that with your newfound knowledge, you can now go ahead and kick some ass. Hope helps this debugging your next issue. We don't have time for questions, but feel free to come around or reach out to me on Twitter. I'll share my slides on Twitter as well. I have one final question for you. Please rate this session in the DevOps app. Be honest, but also be generous. Thank you. Have a great day back.